Hello everyone, I'm Yuto Akiyama, a PhD student from Yamaguchi University. Thanks for inviting me to this conference. Today, I will talk about my recent work for a major big science case, Asian demographics. This is an exciting scientific area to newly resolve a population of nearby supermassive black holes. Let me start with a quick introduction to our scientific motivation. Beck's age and demographic science is strongly motivated by major question in age and astrophysics to understand the evolution of supermassive black hole and massive galaxies. These questions include, how do jets launch and accelerate? How do black hole grow? And how does their growth connect to galaxy evolution? These questions are tightly connected with the inner accretion flow and jet launching near the central black holes. Our understanding of these properties are significantly advanced with the Event Horizon Telescope. EHT can resolve only two black holes, M87 star and Sagittarius star. Despite observing only two sources, EHT has significantly advanced our understanding of the accretion and jet launching. EHT provides direct measurement of black hole masses from their ring diameters. EHT result constrains the black hole spacetime from the resolved shadow. EHT's polarization result resolves the magnetic field structure and reveals the strong magnetization of both two black holes. Bex can make a major breakthrough by significantly improving the angular resolution of the EHT, which is fundamentally limited by the diameter of this planet. With Bex, we will increase the number of resolved black holes from only 2 to about 10, which I will show you later in this talk. So this is a big step forward, and only Bex in space can achieve this resolution. With Bex, we can map out various parameters of the accretion system, including black hole mass, accretion rate, inclination, radiologiness, and the type of the host galaxy. My project is assessing the Beck's capability to measure the key properties of the event horizon scale emission for our demographic science targets, using a bunch of simulated observations. My talk is specifically focusing on these three quantities. First one is the black hole mass. Second one is magnetic field structure, which may encode the information of the black hole spin. Third one is the black hole shadow. Following Dompes's work back in 2022, we adapt three observable proxies to those physical properties. Properties. First, in the event horizon scale emission at EHT and Beck's wavelengths, the source size is directly connected to the shadow diameter, which is about 10 gravitational radii and almost solely proportional to the mass. So we adapt the source size as a proxy to the black hole mass. Second, the distribution of linear polarization angle is strongly reflecting the magnetic field structures. Especially the spiral pitch angle measured with the beta-2 polar Fourier mode is a strong proxy to the degree of the magnetization controlling the overall magnetic field structures. So we use beta-2 as a proxy to the magnetic fields. Third, in EHT images, the black hole shadow appears as the central depression of the ring. We use the central depression as a proxy to the black hole shadow. Next, using those proxies, we first explore to measure those properties, how bright the source should be in radio, and how large the black hole shadow should be. should be. Here in left, we show the estimated number density of black holes as a function of the diameter in horizontal axis and the radial flux density in vertical axis. What we did here is lightly an exhaustive grid search with a numerous number of observational simulations. First, we pick a set of the flux density and shadow diameter and randomly generate ring images. We generated synthetic vector data for each of the ring images, and we estimate the signal noise ratio or SNR of each proxy using its Fisher metric. By repeating these observational simulation over the entire space of the flux density and shadow diameter, we can estimate where a detection threshold of these three proxies for the BEX mission. This method is originally developed by Don Pesci for the ground-based EHT. If you are interested in details, please have a look at this picture. Okay, here I'm showing result. The left panel shows known nearby supermassive black holes that can be observed with BEX in the northern campaign from January to March. Again, as a function of the shadow diameter in horizontal axis and the flux density in vertical axis. The right panel shows supermassive black holes that can be observed with BEX in southern campaign from June to August. You can find three lines in each panel, which shows the detection threshold of red for the size for mass, green for beta 2 for magnetic field, and blue for the central depression for the shadow. If the sources are above of this line, BEX can measure these proxies with reasonable SNRs. What you can read here is the BEX can newly resolve the shadow and magnetic field for about 10 sources and measure the mass for about 25 sources. But of course, here we didn't consider the error in the measurement of the flux density and shadow diameter. The largest source of the potential error is in the shadow diameter, which typically has the error of the factor of 2 or 3 or 11.5 dex. So we also did Monte Carlo simulation to statistically estimate the number of detectable sources against those uncertainties. Here are results. Here we consider the case BEX with scheduled observation of up to 20 nearby supermassive black hole in order of the chance of the success. I estimate the probability for how many sources BEX can actually measure those proxies against uncertainty in the black hole mass. In each plot, the horizontal scale shows the number of observed sources. The vertical axis shows the number of sources where each proxy can actually be detected. Solid line shows the peak probability, and the dashed line shows 10% and 90% confidence limits for the number of detected sources. These figures show good efficiency of BEX observations. If you observe 20 priority target with BEX, you can measure the mass for the most of target and can resolve the shadow and magnetic field for about 10 sources. Okay, so far, our results are based on the simulation using relatively simple geometric models. We also validated these forecasts with detailed imaging simulation using GRMHD models. Here, we use GRMHD simulation by Alice Chan and Angelo Ricaute. In these simulations, the shadow and beta 2 threshold are located at between NGC 4261 and NGC 4552. In the above, we anticipate that BEX can measure all of the source size for mass, beta 2 for magnetic field, and central depression for the shadow. In the below, Vex cannot resolve the shadow and polarization pattern well, but still the source size is expected to be measurable. To confirm our prediction, we also did a synthetic observation of these GRMHD models. And here are the results. As you can see, Vex can reconstruct the overall ring morphology pretty well for the sources above threshold lines. Beta 2 is also very well measured within the accuracy of 30 degree, which is corresponding to 15 degree in the polarization pitch angle. Even if the target of the below shadow and beta 2 threshold, you can see the source size is well recovered in the reconstructions. Overall, we confirm the mass can be estimated by the accuracy of 20 to 30% across the sources above the source size measurement threshold line. So this is the end of the talk and summary. In short, Vex will open a new exiting window in black hole astronomy to resolve tasks of supermassive black holes. Thank you very much for listening, and I'm happy to take any question. Sorry, Peter, so over time.
Oh, it's perfect. We're doing great. You are completely on time. And a very interesting talk. So we have questions from Andrew and then Alex.
Hi, yeah, thank you for the really nice talk. This is, I think, really impressive work, especially the imaging stuff here at the end. So my question is, I think, so this demographic stuff has been interesting to see evolve over time. I think if I remember right, in sort of the initial looks at the ether sample targeted for like NGHT, so only ground-based coverage, some of the claims were like that we would see masses for like 50 black holes and shadows, or magnetic field structure, at least. I guess not shadows because that was never resolvable, but magnetic field beta 2 recovery for like over 30. And so I'm just wondering, it seems like since that was ground-based coverage, we should be able to do less. And do you think the difference there is like we've understood these sources more because of better constraining their properties in the intervening years since that initial NGHT study? Or is it more just the change in methodology? Or yeah, what accounts for that difference?
Oh, so sorry. It's difficult to read English, so please wait. Sorry. And, also, so I think so. You different NGHT or so Vex. Sorry.
Yeah, I guess the question, sorry if I wasn't clear. I think the question was just that this work seems, in some sense, like the most careful look at this that's ever been done, but the results seem more pessimistic than what has been published before, for example, in the NGHT Galaxies paper for what could be studied just from the ground. And so I'm just wondering, is that because we've learned more about the sources, or because the modeling here is more sophisticated, or yeah, what accounts for that difference? And maybe the revision downward in the total number of black holes we could measure these properties for.
I can actually answer that if you want, Yuto. Okay, so the initial estimates from say Dom's paper, and he can also correct me if I'm wrong, were based on general populations of simulated cosmological populations, meaning not specific objects. Whereas in this work, we're looking at the specific objects from ether. It's also possible that there exist more of these out in the universe, and we just haven't identified them yet in terms of having large enough black hole masses and millimeter fluxes. But essentially, I would say that the difference is due to the improvement in our understanding of the actual population.
Okay, no, I didn't appreciate that difference. That makes a ton of sense. Thanks. I think it would also be useful to sort of have equivalent numbers to quote for sort of space versus ground, just to see the improvement, given the sort of new understanding of the populations. But yeah, that makes a ton of sense. Thanks.